Hello and welcome to Set Theory, a bite-sized lecture series. In these videos, you'll get a conceptual overview of set theory that doesn't take all day. If you're new to this channel, be sure to check out the playlist with all the videos in this series, which I'll link to in a card in the corner of the screen. For the past 5 lessons, we've been using an extremely important set without really thinking about it, the natural numbers. Last week, I defined the natural numbers as all the positive integers. But moving forward, we're going to define the natural numbers as all the non-negative integers, so 0, 1, 2, 3, etc., extending forever in the positive direction. First, some things about the natural numbers. The set of natural numbers is written as n. If you know about sequences in series, n is essentially a sequence. It has an initial value 0, and each value after 0 is simply the previous value plus 1. You could even write it as n0 equals 0, nk plus 1 equals nk plus 1 for every integer k greater than or equal to 0. We call this kind of definition, with an initial value and a rule to come up with the next term, a recursive definition. Now, there is an issue with this definition. We're defining the natural numbers using the definition of the natural numbers to get k. Normally, we wouldn't care because we understand what the natural numbers are and we know how to use them. But in fields where we're trying to expand math beyond how we normally use it, we want a rigorous definition so that we can start to think about what other cool properties might be hiding in this normal-looking set. In this video, we're going to construct the natural numbers in 2 related but slightly different ways. The first way harkens back to our very first video about the hierarchical construction of sets. You can click on the card in the corner to watch that video, but the basic idea is that we have some v0, which we'll say for simplicity is the empty set. And each vn plus 1 after v0 is the union of vn and the power set of vn, or vn plus all the subsets of vn. That sounds confusing because it kinda is, but in the scenario where v0 is the empty set, we can sort of cheat a little and say vn is just what you get when you take all the previous v's and put them together in one set. So we're simply going to define the natural numbers as n equals vn, 0 equals v0, 1 equals v1, etc. To actually write that out, that would be 0 equals the empty set, 1 equals the set of the empty set, 2 equals the set of 0 and 1, 3 equals the set of 0, 1, and 2, and so on. Each number n is the set of all numbers previously before it. And so one consequence of that is that you can actually translate the in symbol into a less than symbol. If 2 is in 4 in set notation, then 2 is less than 4. This is a useful way to think about the natural numbers, and it certainly holds up under inspection. It's a valid definition, but it's kind of ugly and doesn't make that much conceptual sense. The second way we're going to construct the natural numbers is also a bit ugly, but in my opinion, it makes a lot more conceptual sense. So the second definition has to do with something called a Peano system. A Peano system is essentially a ladder made of discrete steps in a specific order with a starting point but no ending point. This starting point is called E, and each step of the ladder is the result of applying some function s to the previous step. Side note that I know these letters are super weird, and I have no idea why Peano decided to use them, but we will bravely soldier on. For ease of discussion, we will shorten s of e to s2 of e, and do the same for any subsequent terms. This might be confusing because usually in algebra f2 of x means f of x squared, but since in set theory the concept of next is much more important to us than the concept of squared, we are going to overwrite that notation and use it this way. So e, s of e, s2 of e, s3 of e, etc. We define this Peano system to be the order triple containing some set n, some function s that takes in elements of n and puts out more elements of n, and some starting member of n, e. Furthermore, this triple must satisfy 3 conditions. First, e is not in the range of s. There is no point on this ladder where we apply the function s and it brings us back around to the starting point e. If there was, the Peano system would not go on forever. It would be a closed loop. Second, the function s is 1-to-1. This means that for every input, there is exactly 1 output, and for every output, there is exactly 1 input. This is so that there are no branching paths on this ladder. We want to be able to look at a single step and know exactly where it came from and where it's going. To bring in the natural numbers a little prematurely, it would be terrible if we were counting 0, 1, 2, 3, and then from 3 we could either go to 4 or 5 or 100. Similarly, we don't want to look at the number 3 and wonder, what number led to 3? We want to be 100% sure that the number that came before was 2. The third and final condition for a Peano system is any subset A of n that contains E and is closed under S equals n itself. This is a really fancy way of saying that the ladder goes on forever. If a set A is closed under S, that means for any element x in A, S of A is also in A. You can apply S to anything in it and still get something within it. So this condition says if you tried to take out some of the steps in the ladder and say, yep, this is a fully functional, complete ladder, you couldn't do that. You need all infinity elements in N for the Peano system to be complete. So what does all of this have to do with the natural numbers? Well, we can take our Peano system and create a function associating each term with a number, namely Sn of E equals n. We can visualize this as drawing an actual ladder between this S of E line and the number line. Each term in the Peano system corresponds to a natural number. And because we made all those rules to make sure that the Peano system has a strict order, goes on forever, etc., we know there won't be any weird mix-ups a billion terms in. So this is how we will conceptually define the natural numbers, as a correspondence to a sequence defined by a starting term and a next function. There are a few other important things about natural numbers in the textbook, but I personally didn't find the explanations to be very satisfying, so I may make a follow-up video, or if not, I'll just introduce those topics as necessary. I think the most relevant consequence of this is that we've just shown we can take any ordered list of anything and turn it into 0, 1, 2, 3. You probably already do this on a daily basis, but I find it cool and I hope you do too. I'm also going to link to an AOPS video that I watched in middle school that uses this fact sort of implicitly to do basic counting really efficiently, and that was one of the first introductions that I got into sort of this manipulation of the number line to fit whatever purposes we need. And that concludes the 6th video of this video series about set theory. I hope you enjoyed it. Let me know what you think and if there's anything that would make it better. See you either next week or in 2 weeks, depending on what I do. See you soon, and thanks for watching.